Okay, and Kedar kindly calculated it for us, where sorry, this is just cheating because it was like 0.2, 0.4, 0.4 here, but now it became 0.4, 0.4, 0.2. This is not okay. We will just say okay. So don't worry about this one, but I think we did the calculations correct. Okay, we will send this to Kedar as a note. But anyway, I think I hope we get the idea, right? You just keep expanding out as you get each symbol, you expand out a particular sub-interval in your current interval, right? Okay. Okay, let's look at a pseudocode just so that it's very concrete, right? So the encode block function, the step 1 is to find the interval corresponding to the input. So this is in SCL, as you might guess. So initially you start with low and high as 0 and 1. And then you go over every symbol in your input and you shrink range. So shrink range is really the core function of arithmetic encoding. And what does shrink range do? It starts with the current range and it calculates the new L and the new H. It's exactly like the formula we saw before, represented in a slightly different notation. But yeah, I encourage you to, like here, for example, RNG is like the previous range, right? This thing is probability of the current symbol, right? And the product of these is the next range, right? And you need to keep that cumulative probability table because you need to know where you start, right? So if you look at the example we did, here, right? This 0.2 here is the cumulative probability thing where you need to know so basically at every step you need to calculate the low, you need to calculate the length, and then high is low plus length, which is high. Okay. Okay, any questions so far? This is the encoding and we'll do the decoding in a minute. Actually, maybe let's do the decoding now so that we do a full round trip pass. Okay, so let's say we have this example, 0.3, 0.5, 0.2, and you encoded BACB, and you got this range 0.429 to 0.444. Okay. Point 3, 0.5, 0.2, and your final interval was 0.429 to 0.444. So 0.43 is a number in this range. Do we all agree? 0.43 is a number in this range. Okay. So decoding. So here we are doing decoding. So we again do the same thing where we divide it into 3 parts. So this is 0.8 C. and the number you received is 0.43. Okay, can somebody suggest what is the first symbol? So I'm now decoding. I don't know what I encoded. What would be the first symbol I would decode if I received this 0.43 as my encoding? I heard an A. Can somebody who said A, can you explain why A? I guess those who said B, explain why B.
Since it falls within like the range for B, we know that when we encoded it, the first one we picked had to fit that range. So just going to get any other, any of the ranges.
Yeah, so very good. So the intuition here is that as you encode it, the range only gets smaller and smaller, right? So if you are going to end up with 0.43, you better start with B, because if you started with something else, you will never get to 0.43, right? So your range will get smaller and smaller, right? So it has to be B. It has to be this thing, okay? Now we will again like expand it out as usual. So after you do it, I think it will be 0.39. No. Let's do it carefully. So the length of the interval is 0.5 multiplied by probability 0.3. So it will be 0.45. Then 0.5 times 0.25, so 0.7. After you do all that same, so this is sort of identical between the encoder and the decoder. Okay, now you know your original number you received was 0.43. So can somebody tell me what is the next symbol I should decode? I hear an A from a couple of places, which is correct. Can somebody explain why A? It's very simple, very simple. 0.43 lies in the BA range, that's why, that's it basically, right? At every step you just see the number that you received, where does it lie? Which range, which sub-interval does it lie in? So it lies in 0.3 to 0.45, right? So you see that this lies here. So BA, right? So now you have encoded two symbols. You have decoded B and you have decoded A, right? And I think you can see how this goes, right? Every step, you basically repeat the same process from encoding. You split your sub-interval into sub-intervals. The number you received, you see where does it lie in those sub-intervals, and you decode symbol by symbol, right? Okay, so now what have we seen so far is, so we have seen how you go from sequence to interval back to sequence, right? So we have, yep.
How do you know when to stop? Because you could just keep going and like make up a longer sequence and empty.
So the question is, how do you know when to stop? Like in this example, I could have just gone on and on. With my 0.43, I could have decoded like a billion symbols if I wanted to. There are okay, so maybe let's write it down and clearly answer it. So question is like when to stop decoding. So the first method, which is what we will use, we use in our library, for example, is at the start, I guess, we prepend the length basically n at the start. You just store the length basically. So that is one way. There is a second way which I've seen in some places is you create a special symbol called, you can call it like end of file, for example. So end of file. Then you need to assign, because you created a new symbol, right? It wasn't in your ABC set. You created a new symbol which is end of file. You need to assign it some probability and basically encode your sequence followed by this special EOF token, basically. So there are like two ways to make sure that you can end at the right point. One is that you just prepend the length at the start. So then the decoder first reads the length, it knows how much I need to decode, it will stop decoding at the right time. Or you put this end of file token. If you have done like generative models, LLMs and stuff, they also have a token where, like, how does your chat GPT know like when to stop, right? So sometimes you need these special tokens to know when to stop. Okay, any other questions? I think I went a bit out of order. Some of this might already be in the slides, but okay, anyway. So now there are a few things left to do, right? This is not enough. We need to, the parts that are left are we actually need to put this into bits, right? And then from bits we need to go back to an interval. And then we go to the sequence. So this is the part that we need to fill in. Did you have a question? Okay. Yep. So this is one thing we need to do. And the second thing we need to do is calculate the number of bits you use, basically. The proof that the 2 by n thing, right, that we talked about earlier. Okay. Okay, so first thing we'll do is we'll try to understand what is the interval length. How does the interval length change as we keep on doing the sequence, right? So first observation, which should be very clear if you understood the thing, is that every time we encode, we make the interval smaller, right? So every step is making the interval smaller and smaller. So the question is, what is the size of the interval for a particular sequence? Can you write that down in terms of the sequence or its probabilities? Any guesses? So I hear an answer which is that it is the probability of that sequence. Can you elaborate?
Like, because when you encode, like for the first character,
Yep.
the length of it will be the probability of the first character.
Mm.
You multiply with this interval for the character.
Yep. So the right answer is that, yeah, it is the probability of the sequence, where we are always assuming this IID model, right? That the sequence, the probability of the sequence is the product of the probabilities of all the terms, right? And why is that? Because step 1, you take the interval corresponding to x1, right? So which is like px1, you split it. And then step 2, you take the thing corresponding to px2, and then you split it further. So at every step, you are taking the sub-interval, which is proportional to the probability of that sequence, of that symbol. So at every step, you are reducing the interval according to the probability of that sequence. Let's look at the example, just so we are very confident here. Maybe let's look at this one. So here, after step 1, the length is probability of B, which is 0.5, right? You can verify. After step 2, the length is probability of B times probability of A, which is 0.5 times 0.3. And here the length will be like, I guess, this thing. So 0.5 times 0.3 multiplied by the probability of C, and so on. So every step, the length of the interval is the previous step multiplied by the probability of the current symbol. So it's like every step you multiplied by the probability of that symbol. At the very start, I talked about what we wanted was that for high probability sequences, we wanted larger intervals. And you see already that we are getting that property. If your sequence has a high probability, then every step you will go into a biggish interval. And so overall your size of the interval will be bigger at the end of the encoding. Okay, is that okay? Okay. Right, so here, just what we said just now, that the length of the interval is the probability of the product of the probabilities, which is the probability of the overall sequence under the IID model. Okay. Okay, now we come to the second step, which is how do you communicate the interval, right? Now you made the interval, but how do you communicate the interval? And the simplest idea that comes to mind is, let's just communicate a point in that interval, right? And then the decoder, we saw the decoding process already. So as long as I communicate a point in that interval, the decoder can do its job. And the way we did it was we found like a number which had a small binary or small decimal representation. But here we will do it slightly more formally, but conceptually it's really the same thing. So in this particular example, your interval was 0.429 to 0.444. So what we are going to do is we are going to take the midpoint of this range, right? So at the end of your encoding, right, you did like a few steps, and then you kept on expanding. And at the end, you ended up with this thing, 0.429 to 0.444. So this is L, low, this is H, high, and then we are going to define a Z, which is L plus H divided by 2. So it's the midpoint of the interval, and that is what we are going to communicate. Okay. These are the decoding slides. I think we already did decoding, so let me just skip this, but you can look at these at home. It's basically what we saw. Right, so this step shows that during encoding your interval and the decoding, like basically the encoding and the decoding are very symmetric. At every step you follow the same sequence of steps exactly. As encoding, so decoding. I won't go through the pseudocode now. Okay. Okay, now let's come back to this primer, which is, till now we have been working with decimal number line, right? Because that's just easier for us to think about. But obviously, just like you know that every number can be represented as a binary number, similarly, you can represent any fraction as a binary fraction, right? So how do binary fractions work? So 0.1 in binary is equal to half, 0.01 in binary is equal to 1 by 2 square, and so on, right? So 0.11 in binary will be like half plus 1 over 2 square. So this is like 3 by 4. So this is basically binary. You won't need to do it really, but good to know. You can do it in any base. Okay. So, for example, if you wanted to do 0.3333, this sort of thing. So in binary, it will be like, so 0.3333 is between 0.25 and 0.5. So it will start with 0.1. I think it will look something like 0.01, some sort of sequence, right? And if you don't want to do it, you can use some utility functions in Python or in SCL to do it. Yeah. This is yeah. Don't worry about it. Like this is not okay. Okay. Yeah. So that was just to say that, like, when you want to describe Z, what you do is you represent Z as a binary sequence, right? And then you just send over the entire sequence, right? The binary sequence. But as you know, right, like it's you need a terminating decimal. If you had like right, in math you study that, like, if you write 1/3 in decimal, it's like 0.3333. It never ends. That's not something you can encode, right? So you need something which is finite. So Z's binary representation can be long and it can have like infinitely many bits. So this is not something in practice you can encode. So what we are going to do is, you need a Z hat such that your Z hat is within L and H and it has a short binary representation, right? So we already, like, intuitively we can do this, but we are just trying to do it in a more formal way. Like, how do you prove that you can always find a Z hat which has a small binary representation that lies within this range? So that is sort of what we are going on about here. Like, how do you prove that given a particular L to H, you can always find some Z hat which has a short enough binary representation, right? So let's say K is the number of bits you decide to truncate it to, right? So you find that binary expansion of Z, and then you truncate it to K bits, and then you send those K bits on the other side. Now you come into some sort of like tricky business where, so what we are saying here is, if Z hat has a binary representation something, then not only does Z hat need to belong within, so basically Z hat needs to lie in the L to H range, but if you extend Z hat with some arbitrary binary stuff, that should also lie in the set L to H, right? Otherwise what happens is that there can be doubts about how to exactly decode this. I will not go into the technical details here, but because last year we had a homework question and then it was very hard and we made a mistake and then students made mistakes. But there are reasons basically. If you don't do this correctly, then there are edge cases where decoder will make the wrong decisions. So basically, let me sort of quickly go through this. So the point is that what you need is that Z hat and this whole interval should lie within this other interval. So you need to find a K such that Z hat to Z hat plus 2 to the minus K is within this thing. Okay, I will just skip. I will skip. Okay. This is what you get at the end of the day, that if your length of your interval is H minus L, then you need K, which is this thing, log of 1 over H minus L plus 1. Right? Okay. Apologies for not going over it in detail, but let us do an example and let's try to build some intuition at least, right? So if I have 0.35 to 0.45, let's say, so this has length equal to 0.1, right? And you can find a number which is like 0.4, which lies in this range. Is that, people agree? Right? 0.4 lies in this range, 0.35 to 0.45. Okay, now let's do this one, 0.355 to 0.365. what is the length of this thing? Yeah, 0.01, right? And can you tell me a number that lies within this range? Yeah, 0.36 lies within this range, right? So 0.36 lies within 0.355 to 0.36. Sometimes it's just easier to look at examples. Okay, now let's do one more. Okay, what is the length here? 0.3555 to 0.3565. Yeah, length is just like 0.001 right now. And you can find like a number which is like 0.356 here, right? So what the intuition here is that the number of bits needed is roughly the log of the interval length. That is the intuition I think you will develop. I think if you look at a few examples, it becomes very clear that as your interval goes shorter, you need more and more longer and longer decimals to find within that range. But the length of that decimal is roughly logarithmic in the length of the interval. Yeah, like in this example, you see, right? Like as I made my length 10 times smaller, I needed one more digit. Similarly, if you, in the binary case, if you make your interval 2 times larger, you will need one more bit. And then you make it 2 times larger again, you need one more bit. So that's sort of the intuition here. Okay. Yeah. So, yeah. So quick story here, right? So we studied arithmetic coding when we did our information theory classes long time ago. Intuition is very easy. Basic intuition is very, very simple. Even if you take that away, that's enough. More probable sequence goes to longer intervals, which can be represented with fewer bits. That's it, right? And then we wanted to make this compression library. We wanted to implement it in practice. And then you just run into a million different issues like this, where it's very tricky, complicated to prove. And we haven't even come to like even bigger issues. So, yeah, just be thankful to the people who like implemented it in C for you, and then you can just use it. You don't need to worry about all these details. But yeah, it's a bit tricky. Like there are parts of it I cannot claim that I fully understand. Like we'll come to those later. I think Kedar implemented it, but I think if you ask him today, he would have forgotten probably. So just very, very complicated stuff just keeps coming. Right. So, yeah. So we saw that the size of the interval was log of the probability, right? And we saw that the k was this thing. You get the +2 because you have the ceiling function. And after you basically use this formula. Okay, so this is what you get basically. That the length of the overall thing is less than equal to log of the probability +2. So you're just losing 2 bits for the entire sequence. So this is the main result of arithmetic coding, that if you have a sequence of probability p, then you pay log 1 over p +2, however long your sequence may be. So let's just do super quick. Expected code length equal to the expectation of log 1 over p xn equal to n times, because of the IID-ness, is less than equal to. So what you get at the end of the day is that your expected code length is less than equal to n times the entropy +2. So this is the main result here, that with arithmetic coding, you get your expected bits per symbol between hx and hx plus 2 over n, right? And I think somebody asked at the very, like, towards the start of the thing, where does the 2 come from? And yeah, this is where the 2 comes from. You get 1 from this ceiling function, and you have a 1 here. So that is where the 2 comes from, right? I don't know if it's very adds any intuition, but that's how it comes. Okay, sorry, I have to move a bit fast. Okay, just to summarize, given any distribution P, you will achieve basically within 2 bits of the entropy. Encoding and decoding are linear time, very efficient, right? We saw that only thing you need to do is like you need to multiply some numbers and make those intervals. You do not need to save a large codebook. Neither the encoder nor the decoder actually needs to pre-construct a codebook. You just go on the fly. Every step you just need that interval and you make it smaller. Like one thing to note is you don't even need to compute P sort of xn sort of things, right? You don't need to compute all, like if you have done like Huffman coding, in Huffman coding you would first make a table where what is the probability of AAA, AAB, AAC, BAA sort of thing. You need to make a big table and then you can actually start doing the encoding. Here, nothing. You just need per symbol probabilities and you just go sequentially. And this last point is going to be very crucial in the next few lectures. Don't worry about it for now. Is that here we assume that P was fixed, but you can actually vary P at every step and it still works with arithmetic coding. So it's a very, very powerful algorithm. This is like lecture 8 next week. Okay, in the few minutes we have left, let's talk about a couple practical issues. So as we keep doing this, what do you observe? Do you think you will run into some issues as if you have like 100 length sequence or 1,000 length sequence? What do you see? The intervals, are they looking, yeah, what do you observe basically? Yeah. So one suggestion is that, yeah, like as you go more and more, right, the high and the low are getting closer and closer to each other. Very soon you will run into precision issues because on your computer, if you have a 64-bit float, it can only have so much precision and it's very quick. Like within like 100 symbols, you would run into precision issues where your high and low cannot be distinguished on your hardware. Okay. So any suggestions on what you could do? Let me not ask for suggestions. Let me tell you what you do. You basically, if you reach a point where L and H have become very close, what you do is you say that, okay, if you have any initial digits which are common between L and H, you release those bits. You say that, okay, these bits, so what we are saying here is, let's say you are in this very small range, that's from 0.429 to 0.444. You already know first digit is going to be 4, right? Whatever interval you are going to end up with, you know the first digit is 4. So what you can do is you can release that 4 and you can make a new thing which is going from 0.29 to 0.44. This is just like an illustration. So the idea is that you can keep releasing those bits. You don't need to like keep L and H getting closer and closer. At some point, if you see that L and H have a lot of common prefix, you just release the prefix. This is the sort of thing that gets very tricky when you actually start to implement it. So the idea is that if L and H both start with a common substring, then any value lying within this will also start with this. So you output the bits basically. So it's a streaming algorithm. It's not like you need to wait till the very end to output a single bit. As you go along, you keep on rescaling we will not do rescaling now. Okay, let's keep going. Okay, yeah. If you're interested, I think some of you might be interested in how it actually works. We encourage you to look at the SCL representation and implementation. And what you will see is that the SCL implementation has links to some blog posts, which are basically the only places where you can find a description of the algorithm, like a readable description. So just go to those blog posts if you want to understand. Right here, we are just trying to give you like the high level idea. And in the assignments, you will do some examples. There will be a final project if you want to do some of this in more detail. Right. So there are a few variants here. There is arithmetic coding. There is something called range coding where you work with bytes, so it's more efficient on a computer. A few variants for practical, like for the purpose of this class, all of them are the same, exactly same intuition. Very commonly used. All these image and video coders heavily rely on arithmetic coding. Many of these you will see in the second half of the class, in the lossy compression part. And many of these experimentals, extremely like high compression ratio compressors, they rely on arithmetic coding. And these we will see in lecture 9 basically. So this is second half, lecture 9, okay. Okay, last thing is that arithmetic coding is pretty fast. It's linear time, but it's due to all these arithmetic operations you are doing with multiplications and divisions, it is actually significantly slower than Huffman coding. So here you see Huffman coding and arithmetic coding compared. You see the compression is better for arithmetic coding because you get a bigger block size effectively. So this is good, right? But this is bad. The speeds are not good. So depending on the application, this may or may not be a bottleneck. So the next lecture, which Pulkit will take, you will see two very modern codes. So arithmetic coding was 1970s. These two are like 2010s basically. So in the last 10, 20 years, these have been developed. They, especially this TANS, this is like somewhere between arithmetic and Huffman coding and very fast decompression, still getting the same, roughly the same compression as arithmetic coding. So you will see something very new and novel, which is now used in basically every codec or every compressor built after like 2020 or something, or after 2015 is probably using TANS instead of arithmetic coding because of the high speed it offers. Okay, before I leave, okay, just remember this. None of the else really matters as much, right? The main point is more probable sequences lead to bigger intervals, which lead to shorter bit lengths, right? This is the takeaway. This is what matters in the next, yeah, this is the intuition behind arithmetic coding. And yeah, feel free to ask questions. Thank you.